Do a few more questions. We're going to look at some conceptual questions regarding capacitors. Okay, if the potential difference across a capacitor is doubled, by what factor is the electric potential energy in the capacitor multiplied? So here's the formula. I'm going to use the College Board likes to put a U there. So if I were to double the voltage, that would also double the potential energy. That's the idea there, that to look at that formula and be able to determine what will happen when you double a quantity. Let's try question 2. 2 parallel plates are uncharged. Does the set of plates have a capacitance? Yes. The capacitance depends on the area, the plate separation. It also depends on the dielectric, which has, again, this permittivity value. So depending on what you put between the plates, that can also affect the capacitance. Something that's a better insulator is going to increase the capacitance because it's going to allow you to put more charge on the capacitor. If you were asked to design a small capacitor with high capacitance, what factors would be important in your design? Well, we'd want a dielectric. We'd want small plate separation, and a dielectric would allow us to minimize that plate separation. This question asks about a small capacitor. I mean, ideally, a bigger area would increase capacitance as well, but that doesn't really allow for a small capacitor. Okay, question 4. If the area of the plates of a parallel plate capacitor are doubled, while the spacing between the plates is halved, how is the capacitance affected? So what I've done here is I've started with the capacitance formula, and then in the second one, I've doubled the area and cut the distance in half. And when I simplify that, I get a factor of 4. So the capacitance is multiplied by 4. A parallel plate capacitor is charged and then disconnected from a battery. How much does the stored energy change when the plate separation is doubled? I've got an explanation here, but before I go through it, I'd like to do a little demonstration. So I'm going to start back here. I'm going to decrease the plate separation, and I'd like you to notice the graph at the top of the screen. I'm going to disconnect this capacitor from the battery. Now, when I do that, if the capacitor is insulated from the surroundings, then the charge on the capacitor is going to stay constant. The plates of the capacitor attract each other, so it's going to take work for me to pull the plates apart. And when I pull the plates apart, you'll see the charge stays constant, but the stored energy increases. The stored energy increases because, again, I've done work on the plates. And it seems a little counterintuitive because the capacitance went down. But again, the work that I do gets stored in that capacitor. So, again, I exerted a force over a distance, exerted a force over a distance, and recall that work is FD cosine theta. In this case, force and distance are parallel, so the cosine of 0 is 1. So basically, work is force times distance, and that work gets stored as electrical potential energy. So that's the big idea. Now back to our notability. When the plate separation is doubled, the capacitance is halved. So the capacitance goes down. However, Q stays the same while that capacitance is halved. So if Q is the same while capacitance is halved, then the voltage has to be twice as much to get the same value. Oops. So the voltage doubles. And finally, if the voltage doubles, then the electric potential energy doubles, since the potential energy is equal to 1/2 Q, which is constant, times delta V. And again, we saw that delta V doubles. One thing also to notice here is again, the capacitance did go down, but the voltage went up, and the voltage is squared in this equation if you're thinking about this version of the equation. So we still see that the electrical potential energy is doubled when we double the plate separation. Question 6, why is it dangerous to touch the terminals of a high voltage capacitor even after the potential difference has been removed? What can be done to make the capacitor safe to handle? So there's a charge separation, and there's energy stored in that separation, and we don't want the charges to flow through a person. So what we would want to do is ground it before handling. I'll have to post a video of somebody working on a guitar amplifier. People who work on guitar amplifiers have to be very careful because the capacitors go up to hundreds of volts, and they have to ground them before they work. What happens to the charge on a parallel plate capacitor if the potential difference doubles? So we're assuming here that the C is constant, then Q equals CV. So if voltage doubles, Q must double. So in this scenario, we're connected to the battery. And let's do an example. I'll make the voltage about, I'll try to make it about 0.75. Okay, so there's my voltage, 0.75, and now I'm going to double it. And you can see how when I double the voltage, the charge, and again, I'm looking at this. So last one, number 8. You want to increase the maximum potential difference for a parallel plate capacitor. Describe how you can do this for a fixed plate separation. So assuming that we're not going to change D, we could minimize capacitance to maximize voltage. And the only way to really minimize capacitance would be to decrease the area or to decrease the permittivity of the dielectric. Decreasing the permittivity would decrease the capacitance because the capacitance is equal to permittivity times area over distance. So again, if the plate separation is fixed, our only options are to reduce the permittivity or the area.